Digital Assets for Investors. Chapter 4, Ethereum and Smart Contracts. Section 1, Smart Contracts. A smart contract is a program stored on a blockchain that follows rules automatically once someone triggers it. On Ethereum, that usually means a user or application sends a transaction to the contract, and the contract responds according to the code it already contains. Instead of asking a bank, broker, or platform operator to decide what should happen, the system relies on predefined instructions. If the required conditions are met, the contract can release payment, transfer a token, update a balance, or record an outcome. The key idea is not that the contract is intelligent, but that it is automatic and rule-based. Ethereum became known for this because it made blockchain-based programs much more flexible than simple peer-to-peer transfers. Smart contracts and legal contracts both deal with rules, obligations, and outcomes, but they work in very different ways. A legal contract is written in natural language and often leaves room for interpretation, context, and dispute resolution. If one side does not perform, enforcement may depend on courts, regulators, or arbitration. A smart contract, by contrast, is software. If the coded conditions are satisfied, it executes automatically without pausing to ask whether the result feels fair or commercially reasonable. That makes it fast and consistent, but also less flexible. In practice, many real-world arrangements may still need both: code to automate actions and legal agreements to handle rights, disputes, and responsibilities outside the blockchain. On Ethereum, every smart contract has a few basic parts worth understanding. First is the code itself, which defines the contract's rules and available functions, such as deposit, withdraw, transfer, or vote. Second is state, which is the data the contract stores over time, like balances, deadlines, ownership, or permissions. Third is the contract address, which is the on-chain location users and applications interact with. Wallets and apps send transactions to that address in order to trigger specific functions. So, when investors use a decentralized app, they are often interacting with a contract address in the background, while the app simply provides a more user-friendly interface. People use smart contracts because they can reduce reliance on a central intermediary. Instead of trusting a company to manually process each step, users trust that the code will apply the same rules every time. That can be especially useful in lending, borrowing, trading, and escrow-like arrangements where timing and consistency matter. The better term is usually trust minimized, not trust free. Users still have to trust that the code was written correctly, deployed honestly, and in some cases connected to reliable outside data. So the advantage is not that trust disappears, but that some trust shifts away from institutions and toward transparent, automated rules. A vending machine is a simple analogy for how a smart contract behaves. If you insert the right amount and make a valid selection, the machine releases the item automatically. There is no cashier reviewing your request case by case. A smart contract works in a similar way. Valid input leads to a programmed output. Imagine a token sale contract that checks whether a sale is still open and whether the payment amount is acceptable. If both checks pass, the contract automatically sends tokens to the buyer. The comparison is helpful because it captures the core logic of smart contracts: predefined conditions, automatic execution, and no need for manual approval in the middle. Smart contracts do not run continuously like a web server. They execute only when someone sends a transaction that calls them. A developer first writes the code, compiles it into a form Ethereum can understand, and deploys it to create a contract address. After that, users or applications can send transactions with data, Ether, or both. The Ethereum virtual machine, or EVM, processes the logic for that specific call and charges gas for the computational work. If execution succeeds, the contract may update its stored state and emit events that applications can read. Once that transaction is finished, the contract stops running until it is triggered again. A crowdfunding contract is a good example because the rules are easy to picture. Suppose the campaign goal is 100 EH. The minimum contribution is 0.1 EH, and the deadline is 14 days after launch. Contributors send funds to the contract, and the contract records how much each person has put in. At the deadline, the contract checks the outcome. If the total raised meets or exceeds the goal, The funds can be released to the creator. If the goal is missed, contributors can withdraw refunds according to the code. In effect, the contract acts like an automated escrow system, applying the same divisible rules to everyone. The appeal of automation should always be balanced against the limits of the technology. A bug in the code can be exploited, and because smart contracts often control valuable assets, mistakes can become expensive very quickly. Once deployed, code may also be difficult to change, especially if the contract was not designed with upgrade mechanisms. Smart contracts cannot directly observe the outside world, so they often depend on oracles for prices, events, or other off-chain facts. And because public blockchains are transparent, transaction history and contract activity are often visible to anyone. For investors, the lesson is that smart contracts can remove some operational friction while adding technical, data, and privacy risks. Many smart contract failures come from fairly basic implementation mistakes. A developer might forget to make a function payable, causing Ether transfers to fail when users expect them to work. Someone might hardcode gas assumptions that later break as network conditions or Ethereum design choices evolve. Reentrancy is another classic risk, where a contract sends value out before updating its own records, giving an attacker a chance to call back in repeatedly. Teams also get into trouble when they assume unaudited code is safe or when they rely on weak Oracle inputs. The broad lesson is that automation is only as reliable as the design behind it. Good testing, audits, careful state handling, and healthy skepticism are essential. A useful rule of thumb is to think of smart contracts as blockchain-based automation, not as a complete replacement for legal and real-world systems. They are very effective at enforcing clear on-chain rules, moving assets, and reducing some forms of counterparty trust. But they do not automatically solve issues like fraud, regulation, disclosure, consumer protection, or dispute handling. An investor still needs to ask who built the system, how it is governed, what legal framework applies, and what happens if something goes wrong. That balanced view is important because the strongest opportunities in digital assets usually come from understanding both the efficiency gains and the remaining risks. With that foundation in place, it becomes easier to see how smart contracts fit into the broader Ethereum ecosystem. Section 2. Ethereum ecosystem. The Ethereum ecosystem is much broader than a blockchain used only to send value from one wallet to another. Ethereum provides the base network, but on top of it sit smart contracts, decentralized applications, tokens, wallets, and many supporting services. Developers build dApps that use smart contracts for logic, while users access those apps through wallets that let them sign and send transactions. Assets such as stablecoins, governance tokens, and NFTs move through this environment using shared standards. So when people talk about Ethereum, they are often referring not just to the chain itself, but to a full application platform. That broader view matters for investors because value and risk usually come from the interactions among all of these layers. At the center of that ecosystem is Ethereum as the base layer. It provides the shared security model, the consensus system, and the ledger where final transaction outcomes are recorded. Many different applications may serve very different purposes, but they can still anchor their state changes and settlement to the same underlying chain. That is powerful because it gives the ecosystem a common point of trust and finality. A lending protocol, an NFT marketplace, a stablecoin, and a Layer 2 network can all depend on Ethereum in different ways. For investors, this helps explain why Ethereum is often described as infrastructure rather than just as a digital asset. Around Ethereum, several core components make the system usable. dApps provide the user-facing experience, so people can swap, lend, borrow, trade, or collect digital assets without working directly at the code level. Tokens represent assets and positions, usually following standards that make them easier to move across applications. Wallets allow users to hold assets and sign transactions, which is how they authorize activity on-chain. Layer 2 networks aim to lower cost and increase throughput while still connecting back to Ethereum. Oracles, node providers, indexers, and other infrastructure tools fill in the rest by supplying data, access, and performance support that applications need. A typical interaction starts with a wallet connecting to a dApp. The wallet lets the application see the user's address and, in many cases, read token balances or positions. The app then presents options through a familiar interface, such as swapping tokens or depositing into a lending market. When the user approves an action, the wallet asks for a signature, and that signed transaction is sent to the relevant smart contract. Once the transaction is processed, the blockchain state changes and tokens may represent the new position. That is why it helps to separate roles clearly. The wallet authorizes, the dApp presents the interface, and the smart contract performs the actual execution. Token standards matter because they let assets work across many applications without custom integration every time. ERC20 created a common structure for fungible tokens, which are interchangeable units such as stablecoins or governance tokens. ERC 721 did something similar for unique assets, which is why NFTs can be recognized by wallets and marketplaces that follow the same standard. Because developers can rely on shared rules, a token created in one application can often be transferred, traded, or used in another with far less friction. This interoperability is one of the major reasons the Ethereum ecosystem became so connected. For investors, standards help explain how assets gain utility beyond the app that first issued them. Layer 2 networks extend Ethereum by moving much of the activity off the main chain. Users transact on the Layer 2 environment, where transactions can often be processed faster and more cheaply. Those actions are then grouped and reported back to Ethereum in a way that still depends on Ethereum for security, settlement, or final verification. The practical effect is that many user actions can occur above the base layer, while Ethereum remains the foundation underneath. This design aims to improve throughput without abandoning the trust anchor of the main chain. Because Layer 2 is such an important part of modern Ethereum usage, it deserves a closer look later in the chapter. One of Ethereum's most important features is composability. Because protocols share the same blockchain environment and common token standards, the output of one application can become the input of another. A token received from a trade might be deposited into a lending protocol, tracked by a portfolio app, and later used as collateral somewhere else. That creates a building block effect where services can stack on top of one another instead of being isolated systems. The upside is rapid innovation and flexible product design. The downside, as we will see, is that strong interconnection can also transmit problems across the system. Imagine a user deposits 10 ETH into a yield aggregator. From the user's perspective, that starts in one app with one interface. But behind the scenes, the protocol may route those funds into venues such as Aave for lending or Uniswap for liquidity and trading opportunities. In return, the user might receive a receipt token or LP token that represents the position. Because those tokens follow shared standards, other applications may track them, display them, or even accept them as inputs for new transactions. This is a useful example of how one decision in the Ethereum ecosystem can create links across several protocols at once. The same interconnection that makes Ethereum flexible can also make it fragile. If one protocol contains a bug, dependent applications may be affected even if their own code is sound. If a major service is compromised, losses can spread through connected positions, tokens, or automated strategies. Bridges are especially important to watch because they connect systems and often hold or control significant value. In highly composable environments, failures do not always stay isolated. For investors, that means due diligence should include not just the app you see directly, but also the protocols, bridges, and dependencies underneath it. As activity spreads across Ethereum mainnet and multiple Layer 2 networks, the user experience becomes more fragmented. Investors need to pay attention to which network their wallet is currently using, because sending assets on the wrong chain can create delays, confusion, or extra cost. Not every wallet supports every asset or network equally well, which can make simple tasks harder than expected. External dependencies such as bridges, node providers, and oracles also introduce more points of failure. And high fees can change whether a trade, transfer, or investment move is even worth making. This is a good place to shift into a closer look at gas fees, because cost is one of the biggest practical factors shaping Ethereum usage. Section 3. Gas fees. Gas fees are the payments users make for Ethereum to process activity on the network. Gas measures computational work so every action consumes some amount of it, sending ETH, swapping tokens, minting an NFT, or interacting with a smart contract all use gas because validators must include and execute those transactions. The more work involved, the more gas is typically required. This is why, even though two transactions may look similar from a user's perspective, they can have very different costs under the hood. Understanding gas is essential because it affects both investment returns and the practical usability of Ethereum-based applications. Ethereum charges gas for several reasons at once. Part of the fee compensates validators for processing transactions and helping secure the network. Fees also make spam expensive, which helps prevent attackers from flooding Ethereum with meaningless activity. Just as important, gas creates a market for limited block space. When many users want to transact at the same time, higher fees often move a transaction up in priority, while lower fee transactions may wait longer. So gas is not just a usage charge. It is also a mechanism for security, anti-spam protection, and transaction ordering. It helps to break gas fees into three parts. Gas units describe how much computational work a transaction requires. Gas price describes how much the user is willing or required to pay per unit of that work. The total fee is simply the gas used multiplied by the effective fee rate. A common mistake is to confuse gas units with gas price, but they are not the same thing. One transaction may use many more units because it is complex, while another may be expensive because the network is crowded and the price per unit is high. The total cost of a transaction depends mainly on what the transaction does and how busy the network is. A simple ETH transfer uses 21,30,000 gas, which is relatively small. Interacting with smart contracts often requires much more because the transaction may trigger multiple checks, token transfers, storage updates, or calculations. Writing new data to blockchain storage is particularly expensive compared with simpler operations. On top of that, when demand for block space rises, the price paid per gas unit tends to rise as well. So, total cost increases either when the action is more complex, when the network is more congested, or both at the same time. Ethereum's current fee system, shaped by EIP 1559, separates a transaction fee into two main pieces. The base fee is set by the network and changes depending on congestion. That base fee is burned, meaning it is removed from circulation rather than paid to the validator. Users can also include a priority fee, often called a tip, to encourage faster inclusion. That tip goes to the validator. This structure made fees more predictable than the older auction-style model, even though prices can still become high during busy periods. The base fee moves automatically according to how full recent blocks have been. Ethereum targets about 50% block usage on average. If blocks are more than half full, the base fee can rise for the next block. If they are less than half full, the base fee can fall. The adjustment is capped at 12.5% per block, which helps smooth changes instead of allowing unlimited jumps in one step. Even so, sustained congestion across many blocks can still push fees sharply higher over time. From the user's perspective, a transaction usually begins with a wallet estimate. The wallet suggests how much gas the action may require and attaches a base fee plus a tip based on current network conditions. After the transaction is signed, it enters the mempool, where it waits with other pending transactions. A validator then includes it in a block when the fee level and timing make sense. One important detail is that users pay for gas actually consumed during execution, even if the transaction fails. So a failed transaction may not complete the intended action, but it can still cost real money. Timing alone can make a large difference in cost. Suppose the same token swap is estimated to use 180,000 gas in both cases. During a busy period, a 50 Gwei base fee plus a 5 Gwei tip means the swap costs 0099 TH, or about $29.70 if EH is $3,000. During a quieter period, if the base fee falls to 20 Gwei while the tip stays at 5, the same swap costs 0.45 EH, or $13.50. The transaction did not become simpler. The gas units stayed the same, but congestion changed the fee environment. Complexity can also drive cost, even when the fee environment stays constant. If the network fee rate is 32 Gwei in both examples, a plain ETH transfer using 21,000 gas costs 0.00 TH. A more complex contract action using 200,000.00002C4 ETH under the same exact gas price. So the higher cost comes entirely from using more gas units, not from worsening congestion. This is why investors should be careful when comparing fees casually. Two transactions can happen at the same time, under the same base fee, and still have dramatically different costs because one simply does much more work. Managing gas well is partly about patience and partly about avoiding simple mistakes. It helps to check current fees before making non-urgent transactions, because waiting for lower congestion can materially reduce cost. During busy periods, setting the tip too low may leave a transaction pending for longer than expected. Users also need to watch unit conversions carefully, especially the difference between GUI and EH, because misunderstandings there can lead to costly errors. And it is often wise to compare Ethereum mainnet with Layer 2 options if the same activity can be done more cheaply elsewhere. That naturally leads into the next section, where scaling solutions try to reduce many of the cost pressures we have just discussed. Section 4, Layer 2 Scaling. Ethereum's base layer is highly valuable because it is secure and decentralized, but it does not have unlimited capacity. The network typically handles only a modest number of transactions per second, so during busy periods, users compete for scarce block space. That competition pushes gas fees up and can slow confirmations. As a result, small payments, frequent trading, gaming actions, or other low-value interactions can become impractical on Layer 1 alone. This is not a sign that Ethereum is failing. It is a sign that a secure global settlement layer cannot also be infinitely cheap and infinitely fast at the same time. Layer 2 systems help by moving most activity away from Ethereum while still using Ethereum for settlement. Users send transactions to the Layer 2 network, where those transactions are executed in a separate environment. The Layer 2 then groups many user actions into batches rather than sending each one individually to Ethereum. A compressed record, claim, or proof is posted back to the main chain. This means much of the work happens off the base layer, while Ethereum continues to serve as the final anchor. The idea is to preserve important trust properties without forcing every user action to compete directly for Layer 1 block space. For users, the main benefits of Layer 2 are lower fees and better performance. Because many transactions share a smaller number of Ethereum settlements, the per-transaction costs can drop substantially. Higher throughput also improves the experience for applications that involve frequent activity, such as trading, social interactions, gaming, or low-value transfers. Just as important, these systems still maintain some connection to Ethereum's security or settlement model. That said, the exact level of protection depends on the design of the specific Layer 2. So the benefit is real, but it is never wise to assume every scaling system has the same risk profile. The most important Layer 2 design in today's Ethereum ecosystem is the rollup. A rollup bundles many user transactions together and settles them on Ethereum more efficiently than posting every transaction one by one. This keeps the system closely tied to Ethereum, while lowering cost per user through batching. The two major categories are optimistic rollups and zero-knowledge or ZK rollups. Both use the same broad idea of execute first on Layer 2 and settle to Ethereum later. The difference lies in how they prove or verify that the batch transactions were valid. Optimistic and ZK rollups both improve efficiency, but they reach finality differently. Optimistic rollups assume transactions are valid unless someone challenges them during a fraud-proof window. That usually means withdrawals back to Ethereum can take longer because the system allows time for disputes. ZK rollups, by contrast, submit a cryptographic proof showing that the batch is valid. Because validity is demonstrated directly, finality and withdrawals can often be faster. The trade-off is that ZK systems are typically more technically demanding to build and operate. For investors, this is a good example of how lower fees alone do not capture the whole design story. Not all scaling approaches are rollups. Sidechains are separate blockchains connected to Ethereum by bridges, but they use their own validators and their own security assumptions. That means they may be fast and inexpensive, yet they are not secured by Ethereum in the same way a rollup is. State channels are different again. They work best when a small number of known participants want to interact many times off-chain and settle the net result later. So, while sidechains and channels can both improve efficiency, They solve different problems and involve different trust trade-offs. Data availability is a critical but often overlooked part of rollup security. Posting only a summary to Ethereum is not enough if users and validators cannot access the underlying transaction data. That data is needed to reconstruct balances, verify state changes, and, in some systems, challenge invalid activity. If the relevant information is unavailable, participants may have to trust the operator more than intended. In other words, a rollup is not secure just because something was posted to Ethereum. Strong security depends on whether the network can actually see and verify the data behind the claims. A typical Layer 2 transaction still ends with Ethereum settlement, but most of the work happens earlier. The user sends a transaction to the Layer 2, often through a wallet and app, just as they would on mainnet. The Layer 2 executes that transaction alongside many others and forms a batch. That batch is then posted to Ethereum together with transaction data and either a claim or a proof, depending on the rollup design. Only after the relevant finality process is complete can assets usually be withdrawn safely back to Layer 1. So even though the user experience may feel fast, the settlement path still matters in the background. NFT activity is a good example of where Layer 2 can change economics dramatically. On Ethereum mainnet, a single mint listing or transfer might cost $5 to $10, which can overwhelm the value of lower-priced items. On an optimistic rollup, the user-facing transaction cost might be only a few cents. If 1,000 NFT mints are grouped into a batch that costs $80 to settle on Layer 1, that settlement cost is spread across all users instead of being paid individually. That makes low-value activity much more practical. The main trade-off is that moving assets back to Layer 1 may take longer, especially on optimistic rollups. Different scaling choices involve different trade-offs, so there is no one best answer for every use case. Rollups usually align more closely with Ethereum's security model, which makes them attractive when trust assumptions matter. Sidechains are often fast and cheap, but users depend more heavily on the sidechain's own validator set and bridge design. State channels can be extremely efficient for repeated interactions between known participants, though they are less general purpose. The important comparison points are security, finality, cost, and decentralization. Investors should think in terms of fit for purpose rather than looking only at whichever system advertises the lowest fees. A common mistake is to treat all Layer 2 systems as if they are interchangeable. They are not. Some are rollups that inherit more from Ethereum's security framework, while others are sidechains with different trust assumptions. It is also risky to ignore withdrawal delays, especially when liquidity may be needed quickly or when bridge use becomes necessary. Data availability and fee levels can change over time as well, so lower cost today does not guarantee the same profile later. Good analysis means asking exactly how a system works, what protects it, and where the user is exposed if something goes wrong. Batching can create very large cost savings when activity is scaled properly. If 10,000 transactions were processed directly on Ethereum at 50 cents each, the daily cost would be $5,000. If a ZK rollup can group those 10,000 transactions into 20 batches of 500, and each batch costs $15 to settle, the daily cost falls to $300. Over a full year, that difference adds up to more than $7 million in savings. The exact numbers will vary in real markets, but the principle is what matters. Fewer Ethereum settlements for the same user activity can dramatically improve economics. Section 5. Web3 Infrastructure. A blockchain by itself is not enough to create a full application experience. Web3 infrastructure refers to the broader set of services that help decentralized apps store content, read data, scale activity, and connect users to the network. Ethereum may provide settlement and smart contract execution, but many practical functions still happen through additional layers. Files may live off-chain, transaction history may be indexed for quick search, and outside data may arrive through oracles. Wallets, nodes, gateways, and Layer 2 systems all contribute to usability. For investors, this means a dApp is usually better understood as a stack of coordinated services rather than as code on a blockchain alone. dApps use multiple layers because the base chain handles some tasks poorly, slowly, or expensively. Storing large files directly on-chain is costly, so applications often keep media or other content elsewhere. Reading raw blockchain history block by block is inefficient, so indexing services organize data into forms applications can query quickly. Node access services help apps communicate with the network, while Layer 2 systems improve speed and reduce fees. Oracles bring in outside information that smart contracts cannot observe directly. The benefit is a more usable application, but the trade-off is clear. Every added layer becomes another dependency that can lag, fail, or concentrate risk. It helps to picture Web3 infrastructure as a stack of specialized layers. At the base is Ethereum, which provides consensus, settlement, and the trust anchor for smart contracts. On top of that, node providers such as Infura or Alchemy help applications read blockchain state and broadcast transactions. Storage systems such as IPFS, Arweave, or Filecoin are used for files and metadata that should not sit directly on-chain. Indexing services like the Graph make blockchain data easier to search and display inside an app. Then oracles and Layer 2 networks extend what the application can do by adding outside data and lower-cost execution. When a user takes an action in a DApp, several infrastructure layers often work together in sequence. The front end may load from decentralized storage or through a gateway that retrieves that content. The application then queries indexed blockchain data so it can show balances, prices, history, or positions quickly. When the user chooses an action, the wallet signs the transaction. A node provider relays that transaction to Ethereum or a Layer 2 network, where smart contracts update the underlying state. After confirmation, fresh data returns to the interface so the user can see the result. Oracles fit into the stack wherever a smart contract needs information that does not exist natively on the blockchain. Contracts can verify on-chain data, but they cannot directly observe things like market prices, weather outcomes, sports scores, or election results. An Oracle service supplies that information in a form the contract can use. Chainlink is one well-known example, though the broader idea matters more than any single provider. This is essential for many applications, but it also introduces timing and trust questions. If the Oracle update is delayed or wrong, the contract may execute late or settle on faulty inputs. A decentralized social app offers a useful example of how these layers combine. Instead of a username and password, the user may log in with a wallet signature. Posts and images might live on IPFS so that large media files are not stored directly on-chain. The front end itself could be hosted on Arweave for more persistent access. Activity history may be indexed with the Graph, so profiles and feeds load quickly. Even something lightweight like recording likes could happen on a lower-cost network such as Arbitrum to keep the user experience affordable. Even a simple click on a like button may depend on several systems working in sequence. The content itself may first be loaded from decentralized storage through a gateway. The user's wallet then confirms identity and signs the action. A node provider sends the transaction to the relevant blockchain network. A smart contract records the like on-chain or on a Layer 2. After that, an indexing service updates the visible count the user sees in the app. This is why Web3 apps can sometimes feel slow or inconsistent even when the blockchain itself is functioning normally. The interface depends on more than one moving part. For investors, infrastructure choices are part of the product quality story. A system with more decentralization may be more resilient, but it can also feel less convenient or more complex to use. Lower cost scaling can improve growth and engagement, yet it may introduce new dependencies, such as bridges, sequencers, or specialized providers. Centralized access points can make an app faster to launch, while also creating bottlenecks or single points of failure. Lagging indexers or delayed Oracle feeds can leave users looking at stale information. So when evaluating a Web3 project, it is worth asking not just what the app does, but how the full stack supporting it is built. Many Web3 failures are really infrastructure misunderstandings. Large files usually do not belong on-chain because storage there is expensive and inefficient, so teams need a sound off-chain storage plan. Relying on a single node provider can create outage risk even if the smart contracts themselves are healthy. Oracle updates are not always immediate, which matters when contracts depend on current external data. Indexing services may also lag behind the latest on-chain state, creating temporary mismatches between reality and what the app displays. And with decentralized storage, Content may still exist even when a gateway fails, which means the data is there, but the user cannot reach it easily. A robust dApp is built from coordinated layers that each solve a real operational problem. Ethereum provides the trust layer, but supporting services complete the actual user experience. Wallets connect users. Node providers relay activity, storage systems hold files, indexers organize data, and oracles deliver outside information when needed. Looking at those dependencies helps investors judge whether an application is resilient or fragile. A project with strong contracts but weak infrastructure can still disappoint users and create business risk. The larger lesson from this chapter is that understanding Ethereum means understanding not just the chain, but the full system of automation, fees, scaling, and infrastructure that makes modern Web3 possible.